Okay, so I'm doing the 2013 quiz that you guys did earlier in the week last week. I'm going to try to make this a little bit more in focus. There we go. I went ahead and did the first part because we were all pretty proficient with that. Just let's go back up to the reading real quick. Whenever I see volume, I know that at some point I'm going to multiply that against perhaps a molarity to get to moles. That's one important thing to notice. Also, the word saturated here and here means at equilibrium. One thing that we talked about was the distractor here. This is not going to be used at all in the problem. This is for students who are reading very quickly through this and aren't catching the specifics, like there's still some undissolved MgF2. It's completely fine to take grams and turn it to moles if all of it dissolves. But in the reading, very carefully, it says that the undissolved MgF2 is going to be negligibly small. So because of that, I know I have to abandon the idea of taking this and turning it into moles. So here is my balanced chemical equation. MgF2 is going to be in equilibrium with Mg2 plus ions and 2F minus. Make sure that your number of atoms on each side balance as well as your charges, 0 and then 2 plus and 2 minus is 0. Also make sure that you indicate the state of matter here. The second thing that we did, you can look at it one of two ways. First, I took my moles of F per liter of solution because that's molarity up here, moles per liter. And I multiplied it times the volume here. That volume cancels out and I'm in moles of F. At that point, I look at the ratio. For every 2 moles of F, I have 1 mole of Mg, 2 to 1. And then, 2 to 1 MgF2. And so this is the answer to part 2, which was how many moles of MgF2 actually dissolved. So I'm taking the moles of F that actually dissolved, and I'm using stoichiometry to say, well, if 2 moles of that actually dissolved, it had to come from 1.2 times 10 to the minus 4 moles of MgF2 that dissolved. So that's just using stoichiometry. Right down here, all I did was show you that molarity times volume gives me moles of F. If you'd rather do that, then use your stoichiometry by saying for every 2 moles of F, there's 1 mole of MgF2. Whatever works good for you. All right, the third thing we had to do on part 1 was to tell what is the KSP. So to get the KSP, I had to get some information. Remember that it is products raised to their coefficients over reactants, but in this case a pure solid is not going to be in the equation. So what I'm going to do is I need to know the concentration of this at equilibrium and the concentration of this. So what I can do is say, well, if I have 2.4 times 10 to the minus 3 molar concentration for F, then I have 2 moles of F for every 1 mole of Mg2 plus, which is basically going to give me 1.2 times 10 to the negative third moles of Mg2 plus. Now that I have this, which is my one product, then I also have my F minus is the other. That was already established up here, 2.4 times 10 to the minus 3 in the problem. So I just plug it into the KSP expression here, and you solve for it, and you get 6.9 times 10 to the negative 9. And the KSP does not have a value. It just stays unitless. All right, I then want to move on to the second part, which is a new type of problem. So I'm going to start here, and I'm going to do this one with you guys. So here we have Ca2 plus and Ba2 plus that are present at a 0.1 molar concentration. That means that my Ca2 plus ion is equal to 0.1 molar to start with. So is my Ba2 plus ion. It is 0.1 molar to start with. Okay, it says that I'm going to intend to separate it by adding a 0.2 molar in a F solution drop by drop from a burette. So a burette is just like an eyedropper that has a stopcock on it that you can turn. It lets drop by drop out. It's very, very accurate and precise. And whenever you form the precipitate, you would close the stopcock and then exactly see how much volume you needed to do that. When we get into acid-base chemistry, we will be using burettes a lot, so you guys will have a lot of experience with that coming up very soon. All right, so it says that at 25, the KSP for CaF2 is equal to 3.5 times 10 to the negative 11, and the KSP for the BaF2 is equal to 1.8 times 10 to the negative, 6. Okay. So at this point, they ask us which will precipitate first, CaF2 or BaF2, and why. The answer is CaF2. And the reason is that this number, 10 to the negative 11, has more zeros. It is more negative than this one here. So we're going to say that this is going to precipitate first because its KSP value is smaller. So that means that it would be the first one, because it's a lower number, to exceed that KSP value. All right, so that's going to be part, what is that, B1. All right, for B2, they're wanting to, let's see, assume that the addition of NaF does not affect the total volume. Calculate the minimum concentration of F minus necessary to initiate the precipitation of the salt selected in B1. So I want to know right here on CaF2, what's going to be the concentration of F minus to be able to get to that precipitate. So let's go ahead and write on our rice table. CaF2, again, breaking down into Ca2 plus and 2F minus. I do have an initial concentration here. Remember that my initial concentration for my Ca2 plus is going to be 0.1. So this is going to be 0.1 and this is going to be 0. My change is plus x and my change is plus 2x. All right. So then at this point, we're going to take a look at, since this right here is going to be my value to start with, that is such a huge number compared to the KSP, which is 3.5 times 10 to the negative 11, that I'm basically going to be able to use that as my equilibrium. So my E down here is 0.1 molar for the Ca2 plus. That's really cool, because if I know KSP up here, and if I know my concentration for this at equilibrium, it's very, very simple to plug in and find the value for F. So remember what it is. We're going to say that the CaF2's KSP, which is 3.5 times 10 to the minus 11, is equal to 0.1 times F, right? And then that's going to be squared. Okay? Don't worry about doing the rice table. I just did it for you guys to see that this is going to be my equilibrium concentration. So you can abandon the rice table because now we know what this is. If we know what this is, then we can get to this. So moving this to the other side, we get 3.5 times 10 to the minus 10 is equal to the concentration, sorry, you can't see me, of F minus squared. So all I got to do is take the square root of both sides. So take the square root of this and the square root of that. So I would say that, let's see, 1.9 times 10 to the minus 5 molar is equal to F minus. And basically that's how much F minus ions I have to have in order to get the CaF2 to precipitate from where I start. All right, Roman numeral 3. Almost done. This one says, calculate the minimum volume of the 0.2 molar NaF that must be added to initiate the precipitation of the salt selected in part B. So when you are wanting to know what is the volume of that NaF, what we need to do is do the M1V1 and plug in. So M1 V1 equals M2 V2, right? M1 is always going to be your highest concentration. So I'm going to use the 0.2 molar from the problem. 0.2 molar, and that was NaF times. I want to know what volume that was that made it precipitate. So that's my X is equal to, I know that my M2 is going to be then the concentration of F minus, because we want to know how much is going to get it to that point where it precipitates, and it's F minus that's going to do it, because we already know we've got 0.1 Ca2 plus. So this is going to be our F minus from above, 1.9 times 10 to the minus 5 molar. And then what is our total volume of the situation? So here it said, let's see at the top, does it say how many milliliters? Oh yeah, 500 milliliters. So we'll make that liters, 0.5 liters. So again, that came from the stem. And then all you got to do is solve for X. x should be equal to 4.7 times 10 to the minus 5 liters, or 4.8, somewhere around there, 4.7 or 4.8. Okay, last thing, how would you dissolve a salt that had a limited, that's 3.1, here's 3, the next part says C on the thing. How would I dissolve a salt that had limited solubility? One procedure to redissolve the precipitate. Okay, so we could add water. Adding acid also will help dissolve an insoluble salt. You could increase the temperature. So basically what you're wanting to do is anything that would shift the equilibrium toward the product side to make it dissolve. So that would be the whole quiz. So good luck.